Okay, like we said, gravity gives the universe structure. Like it keeps the Earth spinning around the sun. It keeps the moon spinning around the Earth so that the moon doesn't fly off into space and we don't fly off into space. Okay, by keeping the planets in orbit around the sun. So I put up another little picture here and it shows the gravitational force of the sun pulling on the Earth is huge. Okay, now remember, everything that has mass has gravity. The Earth has mass. So that there's a teeny tiny force of the Earth pulling on the sun. So it's pulling on each other, and because there's this, it's like almost like a ball on a string. Okay, so this gravity is like the string, and it keeps the ball, which is the Earth, spinning around the sun. Okay, now inertia, law of inertia says an object in motion would stay in motion and would continue moving in the same direction. So if there wasn't something to make it turn, the inertia of the Earth would just mean that it would fly off in a straight line and we would leave the sun. So when we say it gives the universe structure, yeah, it's pulling the Earth into orbit around the sun. So it keeps the Earth in orbit around the sun, which thank goodness, because we'd all be dead if we flew off into space and there was no sun and it got, cold and almost absolute zero. It'd be a horrible thing. Okay. Now, this is a review of some concepts that you should have had in elementary school in the 6th grade. Weight is a measure of the gravitational force exerted on an object. So when we talk about our weight, we're talking about how much we're pulled to the nearest thing. So when we stand on a scale and we say our weight is whatever, that's how much Earth is pulling down on us. And we're compressing the springs of the scale. So weight is a measure of the force and is measured in newtons in the metric system. And it's measured in pounds in the standard system. So I put in here how much gravity pulls. A force is pulling you down to the Earth. Weight measures gravity, so it also depends on mass and distance. So the farther you get from the Earth, the less you weigh. So we went up in an airplane and we were flying at a really high altitude, you would weigh less. Now, a lot of times kids get mixed up here because we talk about our weight. And a lot of times, when we say, well, I lost weight, so I got small. And so I fit into a smaller size clothes. You go up into an airplane, and just because you're farther from the Earth, when you stand on a scale, you weigh less. That doesn't mean that you're going to fit into a smaller size of clothes. You didn't change size. All that changed was the amount that the Earth was pulling on you. Like think about that astronaut we saw earlier in the year in the space station. Just because he was in the space station, things looked like they were floating. So if he stood on a scale, he'd weigh practically nothing. That doesn't mean that man lost, like the way we say, lost weight and he practically disappeared. Okay? So weight decreases, like I just explained, as an object moves away from the Earth. When we talk about weightlessness in space, there's almost no gravity. So like that man, he's far enough away from the Earth, there's very little gravitational pull of the Earth. So the things in the space shuttle when we were watching it appeared to float. Okay. It's different than mass. Mass is how much matter is in an object. Weight is gravity's pull. So I made this little picture here. Okay. On Earth, there is more gravity. So whenever we talk about gravity, we're talking about the pull. Okay. I have this thing where this spring is being pulled apart and it's being stretched because the Earth is pulling on the man or the person in the picture is pulling them down towards the Earth. When you stand on a scale, you squish a spring. And what it does is it measures how much you squish it. So either way, it's measuring how much you either compress or stretch a spring. Okay, that's what scales do. So like in the grocery store, they have those weird scales that look like a pan, and you put the vegetables in there. What it does is it measures how much the Earth pulls and stretches that spring. Okay. But on Earth, there's more gravity. So the Earth pulls the person down. You got a bigger force. It pulls this person down more. So we would say they weigh more on Earth. On the moon, where there's less gravity, the moon would pull down on the person less, so we would say they weigh less. The moon has 1/6 the gravity of the Earth. So, for example, me, if I was hanging on this scale and it was in pounds, it would say 240 pounds on Earth, because the Earth would have a strong pull on me and it would pull down with a force of 240 pounds. If I went to the moon, where there was only 1/6 the gravity, and I did the same thing, the scale would show that I only weigh 1/6 as much, or 240 divided by 6, I only weigh 40 pounds. Okay? Now, this doesn't mean that Mr. Palmer would be like, you know, a little skinny, even a little Mr. Palmer. Okay? This just means that the gravity would be pulling down on me less. Okay? Now, mass, the reason why we use a balance is because it measures the amount of matter in two objects. So if we put this person on a scale on Earth, and we found something that had the same amount of mass, the same amount of matter, and they balanced on Earth, well, gravity on Earth would pull down on the person, and gravity on Earth would pull down on this rock, or whatever this thing is, and it would pull down them on the same, okay? Now, we took them up to the moon, okay? They would still balance, because gravity would pull less on the person, and gravity would pull less on this object. So this is why we use mass in science, because it doesn't matter where you go. If you balance something, this is why we use balanced beams to measure mass in science. It doesn't matter where you go if the amount of matter in you stays the same. So just a review of the difference between weight and mass. Weight is measuring how much gravity pulls you down. So like on the Earth, it's measuring how much it pulls us down. Whereas mass measures the amount of matter in something. So the amount of matter in this person is equal to the amount of matter in this object. And no matter where we take them, the amount of matter in each one of them is going to stay the same. So they would balance on the Earth, they would balance on the moon, they would balance if we took them to Jupiter or to Mars or anywhere, okay, or to Venus. Okay. Now, projectile motion. Okay. Projectiles have two forces. They have a downward force due to gravity, and they have a forward force due to thrust. Remember, gravity pulls the same everywhere on Earth. So if we have an example, we have two objects. One is shot, and at the same time, the other one begins to fall. So it's saying this gray one, you know, like if this was a cannon or something, and these were two cannonballs. The gray one gets shot out and is going forward. And at the exact time that it comes out of the barrel of the cannon, the second cannonball begins to drop. Which one would hit the ground first? Well, the gray one has two forces acting upon it. It has thrust, which is pushing it forward. And it has gravity that's pulling it down. Now, the brown one also has it. There's the same, you know, like the two identical cannonballs. The brown one has the same gravity pulling it down. So if gravity is pulling both of them down the same, they're going to hit the ground at the same time, okay? Because gravity on them is the same, so they're falling. Now, this is sometimes hard for kids to imagine, because this one is traveling forward so fast it goes a long ways out in the amount of time that it takes to fall down. It's the same thing as if a bullet dropped at the same instant a bullet came out of the barrel of the gun. The one dropping to the ground would hit the same time as the one being shot out of the gun. So the thing is the bullet is just traveling so fast, it goes a long ways in this amount of time. Okay, since they're pulled to the Earth at the same rate, they'll hit the ground at the same time. Okay, so this is this little clip where Mythbusters actually tested this. They drop one bullet at the same time they fire one. Now, one of the things you got to remember is the bullet has to be going exactly parallel to the Earth. If it's pointing up or down, it's going to change things. So it has to be exactly parallel to the Earth at the same time. If you give it elevation, it's going to change things.
Is needed to match the solenoid. Everything's hot. Let's do it.
So one bullet's going to come out of the gun. They've got this electronic machine rig that it's going to drop the second bullet at the time the first bullet comes out of the gun. Now, if you'll notice, they can't get this machine exactly perfect. They get it pretty darn close. So, it's within human error.
And after a few test fires and a bit of fine tuning, it works.
Bullet piece done. Oh, it's good. It's good. It's 1/3 of a millisecond difference.
I noticed that there's going to be 1/3 of a millisecond difference here. So over the time that it falls, it's going to get exaggerated a little bit. But within this human error, what should expect.
Wow. That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone.
Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here.
Okay.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
So they moved the part of the machinery, the apparatus that drops the bullet down here to where they expect the one that gets fired from the gun to land, so that they'll both be in the picture at the same time.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it.
So it's milliseconds difference, and that's, the only difference it would really be is that it started off just a little bit tiny difference.
It's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.
Okay, I want you to answer these questions on your own, and then we're going to pick up here next time. I hope you're having a great day, and we'll see you soon.